Chapter 28 comes at the end of the text in part because these reactions are reactions that have been discovered in the last 30 years or so, 30 to 40 years, and they have, leaving them here till the very end doesn't really do them justice because many of these reactions are used so much more in labs and in actual chemical synthesis in industry than many of the reactions that you've learned. How many times have you used H2SO4 as a reagent in this class? Only to learn that nobody does that in an actual pharmaceutical chemistry synthesis of a drug. Why? Because H2SO4 is going to mess with all kinds of other functional groups. It's dangerous. But there are some other reactions that are very, very popular. We're going to learn about the Suzuki reaction, which is one of the most done reactions in the world today. And yet it's sort of at the end of this text and as an aside. And so, so we do want to spend some time talking about these reactions. Most of you will never do these reactions unless you join an organic synthesis lab, but not talking about these reactions would be like going to a biochem or bio class and not talking about CRISPR-Cas9 and gene editing. It's like modern stuff that's new, but it's revolutionized stuff, and so you need to have at least heard of it so that when you say you've taken an OChem class, you won't be embarrassed when you don't know about some of this stuff. And I have to say, some of this stuff is outside my area of expertise because I'm not really a total synthesis or methodology organic chemist. I'm a bio-organic chemist. I study peptides and protein folding, and that's fine. I'll tell you sort of as much as I know about this stuff. What we do is going to be just scratching the surface, but it's interesting because it does open up some new doors to synthesis. Okay, so it would be useful for you to review the kinds of reactions that we've done before that make carbon-carbon bonds, and there have been a ton of them in 352. I'll highlight a couple of recent ones that we learned how to do. You learned Friedel-Crafts alkylation, which made a bond between an sp2 hybridized carbon of an aromatic ring and an sp3 hybridized carbon of an alkane. We'll just do a simple Friedel-Crafts reaction. When thinking about carbon-carbon bonds, it can be useful to think about the hybridization of the atoms that are involved in the bonds, just to sort of classify different situations. I'm going to call this one aryl for AR, an aryl carbon. AR means an sp2 carbon in an aromatic ring. And then this one is sp3. So we've done that before, and that works pretty well. There's also Friedel-Crafts acylation, which now involves not an aryl sp3 bond, but an aryl sp2 bond, where the sp2 carbon is part of a carbonyl. So we've got decent solutions for that, but what if we wanted to make a bond between two aromatic rings? What if we wanted to make an aryl-aryl bond? So suppose I'm just making stuff up at this point. What if we wanted to do this, an aryl-aryl bond? We got nothing, okay? What if we wanted, so far, we have no way to do this. What if we wanted to make an aryl-vinyl carbon-carbon bond? So I'm going to use vinyl as an sp2 carbon in an alkene. We actually have done that before That was a little tricky though. It was multiple steps. To do this previously, we had to do a Friedel-Crafts alkylation followed by radical bromination and then finally elimination. It would be nice to be able to do that in a one-step reaction versus a three-step reaction. To say nothing of the fact that radical bromination, if you've got other functional groups in your molecule, there's the potential for some other undesired reactivity. So it turns out modern organic chemistry has some solutions for this. Aryl bonds, aryl vinyl bonds. But it doesn't involve the typical kinds of things that you've seen so far. A lot of the reactions that we've used so far, especially reactions involving catalysis, have involved acids, protonating something to turn it into a good leaving group, or in the case of the Friedel-Crafts reactions, we used Lewis acids, which in many cases were a metal with an empty orbital on it. The reactions we're going to do in this chapter also involve catalysts, but they're not about proton transfer, and they're also not just simple Lewis acids. It's deeper than that. So to understand that, we need to dig in a little bit into transition metal chemistry. I could show you these reactions, and you could memorize the reagents and memorize what they do. Which would be okay, and some people teach it that way. But it's nice to know a little bit more. Sometimes knowing how helps you remember what without memorizing. So we need to do a brief overview of transition metal chemistry so that we can understand the new modern reactions that can make these aryl-aryl and aryl-vinyl type bonds. So, chemistry of transition metals. You thought this was an OChem class. Fortunately it is. We're not going very deep into what transition metals are or what they do. I have on my phone a little app called, it's a game, it's a dumb little game called Atomus. I don't know if you've ever played this. You fuse atoms together. It's helped me learn sort of some of the elements in order. I don't know all of the transition elements. I know some of the first row ones, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. And if you take the column number, this also tells you the number of valence electrons each metal comes with. I don't have this memorized, and fortunately on my exams you'll have a periodic table, so you'll need to be able to use that information. There are, of course, other elements there. I'm going to stick to ones that seem to be more important for modern organic chemistry reactions. One row down from chromium is molybdenum. One row down from iron is, am I getting that right? Yeah, ruthenium. And then one row down from that is osmium. You have seen osmium before as a reagent in was that 351, syn dihydroxylation. We didn't talk about the mechanism there. It was an oxidizing agent. One row down from cobalt is rhodium. There are lots of reactions involving rhodium, and it's next down the column, one row down, iridium. We won't talk about any of them in this class. One row down from nickel is palladium, and we'll talk about palladium a lot. And then one row down from palladium is platinum. There are reactions that involve platinum. We won't talk about them at all in this class. But this is, the numbers here represent is column in the periodic table, but also represents the number of valence electrons. Transition metals on the left-hand side of the table are called early. Those on the right-hand side are called late. And in general, you can see that the early transition metals tend to be electron poor, meaning they have fewer valence electrons. What I've shown you here is the number of valence electrons each metal would have in its zero oxidation state. So the early transition metals are generally electron poor. The late transition metals are generally electron rich. And of course, each of these metals can sometimes adopt multiple oxidation states, meaning maybe a metal doesn't have the same number of valence electrons, maybe it has fewer. You've seen in the electrophilic aromatic substitution, we used an iron chloride complex where iron was in the +3 oxidation state. We're going to talk now about how to look at organometallic complexes, that is, molecules that involve a metal center bonded to multiple things, and be able to determine what the oxidation state of that metal is and how many valence electrons it has. All right, questions so far? So let me show you an organometallic complex. An organometallic complex involves a metal, that's the metal part of organometallic, and then a carbon-containing part, that's the organo part. So here is the metal palladium, and I'm going to show a complex between palladium and 4 molecules of triphenylphosphine. The geometry of metal complexes can be complicated, and that's beyond the scope of this class. If you want to know more about that, you got to take Chemistry 514, Inorganic Chemistry, and PChem. No, yeah, that's okay. I didn't think so. So we're not going to worry about metal hybridization or complex geometry in general. We don't need to so much for our purposes. This is an organometallic complex. This is the metal center, the palladium, and then these molecules are each called ligands. Ligand is the word for something that is bound to a metal. I think that's from the Latin word ligare for tying to something. So the metal is bound to the ligand is bound or ligated to the metal. Notice, if you're thinking, you should be sort of uncomfortable at this point because you're in an OChem class, but even beyond that, triphenylphosphine has a phosphorus bonded to 3 phenyl groups. In this ligand, the phosphorus is bound to the metal. Phosphorus is 1 row down from nitrogen. When we have 4 things bonded to nitrogen, the nitrogen has a positive formal charge, right? So why doesn't the phosphorus have a positive formal charge? The answer is we changed the rules. Formal charge assignments are not necessary in organometallic complexes. You have to show the overall charge on the complex, but you don't have to assign formal charges on any of the individual atoms. So because I did not show a formal charge on the complex, you can assume here that the complex is neutral. Why? Because overall charge was not shown. The second reason that you know that you don't need to show formal charge on the ligands is that we're going to assume that the electrons in the metal ligand bond belong to the ligand. In other words, when I look at this, I know that these two electrons come from a lone pair on the phosphorus, and they didn't come from the metal palladium. That sort of resolves the whole formal charge issue. Not needed to show formal charge on individual atoms, but you must show the overall charge if it's non-zero. Okay. The second thing that will help you with organometallic complexes is to understand that we're going to see two different types of ligands. This is like the world of Pokemon, an ice-type Pokemon or a fire-type Pokemon. Those guys are laughing all the way to the bank. All you have to do is make up some word and then draw a cool picture and then say this is another word type Pokemon, and then people will pay money trying to get it. I don't know. Two different types of ligands. There are L-type ligands, which are neutral ligands. Generally, these involve lone pairs or pi bonds that coordinate the metal. And then you have X-type, which are negatively charged ligands. So you sort of have to know what kinds of ligands you can encounter. The X-type ligands are anions. So I'm going to draw what they are when they're not bound to the metal, but when bound to the metal, it would look like this. And the metal might be bound to other things. We're not going to even draw what those other things are. But an X-type ligand, say hydroxide bound to a metal, would look like that. Same thing for halides, F minus, Cl minus, Br minus, etc. I minus, this would be a metal halide bond. Carbanions, so an alkyl group. I'll give you maybe one example of this. This may be for example, a CH3 minus group. This would be a metal CH3 bond. For all of these X-type ligands, you would assume that the electrons in the metal ligand bond belong to the ligand, and you would see therefore that if the ligand left, it would leave as the negatively charged group. Let's see, are there other X-type ligands? Sure. Anything you can think of that's negatively charged. You might see, for example, a negatively charged nitrogen ligand that when bound to the metal would look like this, or you might see a thiol ligand which when bound to the metal would look like that. Okay? X-type ligands are ligands that when they leave would be negatively charged. L-type ligands are ligands that if they leave from the metal would simply be neutral. So triphenylphosphine is one of those. Ammonia or other amines are also examples of X or L-type ligands. When bound to the metal, it's the lone pair that donates into the metal, and when they leave, they would be neutral. Water is an example of an L-type ligand. A carbonyl oxygen with a lone pair can chelate and coordinate a metal. That's an example of an L-type ligand. Interestingly, even a pi bond can be an L-type ligand. So I'm going to illustrate that by highlighting one of the pi electrons from this carbon-carbon pi bond, that can actually coordinate to the metal. And so the difference between L and X-type ligands is that the X-type ligands leave as negatively charged things, the L-type ligands leave as neutral things. Questions about that? I'm going to show you why it matters. You don't care yet at this point. You may not care after I show you why it matters, but it's important to have that distinction between L-type and X-type. Yeah? Yes. So you have actually seen X-type ligands in a transition metal complex before with cuprates. This is diethyl cuprate. Those are X-type ligands. Because if they left, they'd be negatively charged. Yeah. So we're going to actually talk about that in a second. Let's actually do that with the cuprate. The cuprate is negatively charged. So let's work through this. Overall, the charge is negative if you have two X-type ligands. So that must mean that the copper has a +2 charge on it, right? Or rather, sorry, a +1 charge on it. Because the overall charge on the complex, the way we would draw this actually is a negative charge overall. You have two R- or X-type ligands. Your overall charge has to be the sum of the charges from the ligands and the charge on the metal. So if the overall charge on the complex is -1, and you have two X-type ligands, -2, the only way you get -1 overall is if copper is +1. Okay? So I just told you how to identify the oxidation state of the transition metal. You do that by comparing overall charge on the complex versus the charges on the ligands, and the metal has to have a charge that's consistent with that. I'm not going to bother writing an equation. Do you guys get the idea? Overall charge is -1. You have two X-type ligands, which is -2. In order to balance that out, the metal must be +1. Okay? All right. So that means this is copper in the +1 oxidation state. Let's look at what the implications are for copper. Going back here, copper normally comes with 11 valence electrons. Copper neutral, or maybe we can say copper in its 0 oxidation state has 11 valence electrons. Copper in the +1 oxidation state should therefore have how many? This is arithmetic even I can do. 10 valence electrons. All right? And even though, if you look at the table, 2 of those look like they're in s orbitals, it turns out that in transition metal complexes, they're all going to be in d orbitals. So we have a way, the way we talk about this, copper has 10 valence electrons. We say copper is a D10 metal. It's got 10 electrons in its d orbitals. Now those 10 d electrons aren't the ones that are in these copper carbon bonds. Those are from the ligands, right? All right. Let's do another complex to illustrate this, and then we'll sort of come back and try to answer any questions you might have. Here is a complex you might have seen in general chemistry. This is a complex between cobalt and 6 NH3 groups. NH3 is what kind of ligand? X or L? Right, you have 6 NH3. These are neutral L-type ligands. The overall charge on the complex is 3+. Therefore, what is the oxidation state of cobalt? Therefore, yes, it has to be cobalt 3. All right? That's not so hard, assigning metal oxidation state, if you know that it's a L-type versus X-type ligand. Okay? Each of these 6 ligands is neutral and a neutral L-type ligand, so the overall 3+ charge must be due to cobalt. If cobalt's neutral, it's in the 0 oxidation state, but this is cobalt 3+, therefore it's cobalt 3. Going up to our periodic table, cobalt normally comes with 9 valence electrons. So 9 valence electrons minus 3 for the oxidation state tells us we have 6 electrons, 6 valence electrons. Therefore, cobalt 3 is a D6 metal. It's got 6 electrons in its d orbitals. Okay. Now let's think about the complex overall, because you're used to thinking about carbon and other first or second row elements where you're limited to an atom being surrounded by 8 valence electrons. Clearly here, there's more going on than that. How many electrons surround cobalt? You got the 6 that are on the metal, and then how many more do you have from the ligands? You got 6 times 2 electrons from the ligands. I already wrote that. So that would be overall, this is an 18 electron complex. And that is a complex that we are going to call coordinatively saturated, meaning there's no room for any additional ligands. How can you tell? If you look up at the periodic table, that 1, 2, 3, 4th row has 18 spots in it. That means in the 4th row, including the 4s or the 4s orbital, the 5 3d orbitals, and then the 3 4p orbitals, you've got spots for 18 electrons. So in some ways, this cobalt complex sort of has a noble gas type configuration, and you can use that, you can use the number 18 as a way to gauge whether an organometallic complex is fully saturated or whether there's still a spot for a ligand to bind. Let's go back and do this for palladium, tetrakis triphenylphosphine. That's 4 triphenylphosphines attached to palladium. The overall charge is neutral. These are all L-type ligands. What is the oxidation state of palladium? 0. Has to be, right? Overall, it's neutral. Neutral ligands, 0 oxidation state. Let's go back to our periodic table. How many valence electrons does palladium normally have? 10. So palladium is a D10 metal. Now, how many electrons are in the complex? Well, let's see. You've got 10 from the metal plus 2, 4, 6, 8 from the ligands. There's that number, 18. So this is also coordinatively saturated. meaning there's no place for something else to bind. That's going to explain some of the steps we're going to see in transition metal chemistry. You're going to see sometimes one of the ligands that's on the metal has to leave first before anything else can happen. You're going to wonder, why are we bothering to do that? Why don't I just have something else come hover and bind to the palladium? And the answer is there is no space for that. For transition metal complexes, 18 is the new octet rule. And so you can use that to tell whether a step you're proposing is reasonable or not. Let's do another. And there are going to be, your next exam, exam 4, this is what you want to worry about. There are going to be some questions about transition metals. What is the oxidation state? How many d electrons does it have? Is this metal coordinatively saturated? I've shown you how to answer that. Now, the tough part is you're not going to get this from your text, and there aren't going to be practice problems in your text on this subject. You'll need to work on that based on the examples that I've given you here. And as we go through mechanisms of these reactions, which I'm going to introduce, I want you to pause at intermediates along the mechanistic pathway, and I want you to ask yourself, we won't do this in class. I'll leave them to practice problems for you, but I want you to ask yourself, what is the oxidation state of that metal? What is its d electron count? How many electrons are present in the complex overall surrounding that metal? And is it coordinatively saturated? Okay, let's do a couple more examples. We'll stick with palladium, because palladium is the catalyst of choice in several of the reactions that we'll introduce. This is a new complex that involving palladium that you haven't seen before. This is also a new and interesting ligand. Some ligands are what we call bivalent. That means they can bind a metal in multiple places. The ligand here, what I've drawn for you, is the structure of palladium diacetate, or palladium acetate. It's interesting because it's got two acetate ligands. On this side, the acetate ligand is X-type, because if it left, that oxygen would be negatively charged, right? But here, it's L-type, because the electrons that are forming this palladium-oxygen bond come from the lone pairs on that oxygen. So acetate is a ligand that, as I said, is bivalent. On one of its oxygens, it's X-type, and on the other oxygen, it's L-type. So with that in mind, as I told you, the overall complex here, I haven't drawn a charge, the overall complex is neutral. Therefore, what is the oxidation state of palladium? Two L-type ligands, two X-type ligands. Complex is neutral. If both of the acetates left, they'd leave as acetate minus, right? So the oxidation state must be +2. Okay? How many d electrons? Well, you got to go back to your periodic table. You got to count, or we'll go up here. Palladium normally comes with 10. It's lost 2, so this is a D8 complex. Overall electron count, let's see, 8 plus 8, 16. So not coordinatively saturated. There is a spot for another ligand. Okay. Let's do one more palladium complex, and then we'll start diving into chemistry or reactions. Looks sad, right? there would be a very small but devoted market for OChem-based emojis. Like if you want to make emojis that look like benzene rings but that express emotions, as I said, it's not too many people, but they would be extremely devoted to you. Okay. I told you before that alkenes can be L-type ligands because the pi electrons bind to the metal. Drawing that is difficult. The best you can do is to draw the pi bond like that, sort of perpendicular to the metal, and then draw a dotted line, sort of indicating that the pi electrons are binding to the metal. So you sort of have to know what you're talking about to interpret these complexes. Okay, what type? Overall, I've shown you the complex is neutral. There's no charge. If there had been a charge, I would have put a little bracket here and drawn the charge, but I didn't, so you know it's neutral. Let's go through what type of ligand is triphenylphosphine? L, good. Neutral, neutral. Alkene is neutral. How about the benzene ring? X. You can tell because if it left and took its electrons with it, it would be deprotonated benzene. So that's an X-type ligand. And then Br is also an X-type ligand. Therefore, what is the oxidation state of the metal? It's palladium 2 again. Good. D electron count, we just did something with palladium 2, so by analogy, that's a D8 metal. And then overall electron count, 8, and then how many ligands do we have? We got 2 electrons from ligands, 2, 4, 6, 8, 10. So this is overall an 18 electron complex. It's coordinatively saturated. There's no place for more. If we wanted to do something first, one of those ligands is going to have to dissociate. Okay, good. So that's your introduction into organometallic complexes. We're doing this because this is going to help you understand what's going on in the metal, what's going on with the reactions that we're going to talk about, because there are going to be 2 new mechanistic steps, at least 2, maybe more, that are totally new. You've not seen reactions like this before. And understanding them is a little bit easier when you understand metal oxidation state. So the first new reaction is called, and I need to turn off my atom game, it's just sitting here staring at me, tempting my attention. So the first new organometallic reaction is called cuprate coupling. You've done some things with cuprates before. This is a new reaction. So here is a cuprate reagent. And overall, the complex on the metal, the charge on the complex is -1. There's a counter ion, lithium. So that's the cuprate reagent. And your starting material is a halide. For example, this aryl halide. Okay, let me just pause by saying these reactions are in your text, even though the stuff about oxidation and transition metals isn't in your text. So you'll be able to get practice on these reactions, predicting the products and synthesis as you look at your text. I'm going to be pretty quick at going through the cuprate reaction because it's not the most interesting thing that we do. This reaction makes a bond between the carbon that had the halide and the carbon that was bonded to the cuprate. So this is going to make a new carbon-carbon bond. I'll draw that here. And then one of the 2 carbon groups on the cuprate is going to be bonded to the carbon that had the halide. The mechanism, however, is not SN2. Of course, you probably didn't think it was because you're looking at that alkyl halide, or sorry, this aryl halide, and you're thinking, all right, already I know that I can't do an SN2 on an aryl halide. But it turns out that this reaction works on alkyl halides as well to make new bonds between sp3 carbons. And you could be easily tempted to predict that the reaction mechanism for this reaction below would simply involve copper acting as a typical the cuprate reacting as a typical organometallic reagent and having the electrons leave and dump into the sigma star. That doesn't appear to be what's happening here. It's different from that. So let's learn about that. I'm going to copy this cuprate complex here. And then let's just do the aryl halide. What I'm going to show you, it turns out people often don't push arrows with transition metal chemistry, in part because with transition metals, nobody bothers putting in all the d electrons as lone pairs. You could, but nobody does. And so when you're dealing with transition metal chemistry mechanisms, the background that we just talked about is highly useful. I am going to push arrows to help you, but understand that your text might not. So what happens here is what's called an oxidative addition step. I'm going to show you the products of this oxidative addition step. And this is a new type of reaction mechanism that you haven't seen before. I'll show you the products. We'll count oxidation state before and after, and then we'll sort of go about pushing arrows. So here's what the complex looks like after we do the oxidative addition step. Copper will now be bonded to 4 things. Okay, and overall the complex is still minus. So let's do what we've done with transition metal complexes before. Let's go before. The cuprate reagent has, and we actually did this before, so we don't need to review this. It has 2 two X-type ligands, 2 R groups that'll leave as negatively charged groups. The overall charge on the complex is minus. Therefore, copper is in the +1 oxidation state. If we go up to our periodic table, copper normally has 11 valence electrons. That means this copper must have 10 d electrons, and overall number of electrons in this complex is 14, right? Let's go here. We had 2 X-type ligands. Now, after the oxidative addition, we have how many X-type ligands? 4, right? That means if all of those ligands left with their electrons, we'd have 4 negatively charged ligands. To balance the charge on the complex, what must be the oxidation state of the metal? It's got to be 3. Okay? Copper has to have gone up 2 steps in oxidation state. We call it an addition step because the bromo and the phenyl group got added to copper. We call it oxidative because copper went up by 2 in oxidation state. Let's count the d electrons that copper has, therefore. Copper normally comes with 11 minus 3, it's got to have 8. Copper formally lost 2 d electrons. Overall, how many electrons are in the complex? Well, 8 on the metal plus 2, 4, 6, 8. So overall, 16. The complex has more electrons by 2, but copper has 2 fewer electrons. What happened? Well, what must have happened is that 2 of the d electrons on copper formed a bond with carbon at the same time as the 2 electrons from the carbon-bromine bond were forming a bond with copper. That's not an SN2 reaction. That's 2 things going on at once. The transition state for that reaction probably looks something like this. Probably you've got copper and you're forming a new bond with bromine at the same time as you're forming a new bond with the benzene ring carbon at the same time as the benzene ring carbon is breaking its bond with bromine. The overall double dagger here indicates that it's a transition state. The overall charge is -1. Okay, so it's not really an SN2 reaction at all, but it involves 4 electrons all in the same step. 2 of the electrons come from the carbon-bromine bond and 2 come from the metal. But after that reaction, those 2 that are from the metal count as though they belong to the X-type ligand. That's the oxidation state. The ligand basically now owns 2 electrons that used to belong to copper. And people can calculate using molecular orbital theory and quantum mechanical methods, they can calculate just how uphill versus not this type of reaction step is. You will see this kind of oxidative addition step again and again and again in this chapter, and you ought to recognize it. And the way to recognize it is to follow the change in oxidation state of the metal. People will generally not push electrons like this. One reason they will not do this is it is impossible to tell whether the electrons from copper went to the copper-carbon bond or whether alternatively they went to the copper-bromine bond and then the electrons from the copper-carbon bond went to the copper. You can't tell. It's the same either way. My dad used to say it's a horse apiece, which always made sense to me because my dad said it. I don't know if you've ever heard that phrase. I don't even know what it means. We'll Google it at some point, but all right. That's step 1 of the cuprate addition, or sorry, the cuprate coupling. Step 2 is going to involve the formation of the carbon-carbon bond. So step 2 is going to involve, we're going to start with this copper 3 complex, and then afterwards, I'll draw you what the products are. This step is called reductive elimination. It is sort of the opposite of oxidative addition. I'm using pink for the new bond. Okay. So our product is with this new bond between one of the alkyl groups and the benzene ring. Let's look at the complex that we have afterwards. These are both two X-type ligands. The overall charge on the complex is -1. Therefore, you can tell that copper is now back to the +1 oxidation state. You can therefore tell that copper has 10 d electrons. In other words, copper got 2 of its electrons back. And you can tell that the overall electron count is 14. What happened in this reductive elimination reaction? I'm going to erase the blue and the red now. We'll make this one red and this one blue, or, well, what appears to have happened, and again, there are going to be two distinct ways you can push the arrows here, and it's not at all clear what the right way is. Electrons from one of the copper-carbon bonds come over to form a new carbon-carbon bond. At the same time, the bond between copper in blue, between copper and that metal breaks, and those electrons go back onto copper. It's entirely impossible to tell whether the arrows should be pushed that way versus this way. It's, as my dad used to say, a horse apiece. The transition state for that reaction should look something like this. The copper bond between copper and benzene is breaking. My dad's still alive though, so I guess used to makes it sound, that imperfect tense sort of makes it sound like he's no longer with us. But he still is, and he still does say a horse apiece, and I'm still not sure on the etymology of horse apiece. And now that I've said that word, I kind of like sometimes to say entomology when I mean etymology, just to see if anybody catches it. All right, so the transition state for this reaction looks like this. The bond between copper and each of the ligands is breaking at the same time as the new carbon-carbon bond is forming. And that gives you your product, okay? Oxidative addition, reductive elimination to give you the product, and this is a coupled product, and this reaction is called a cuprate coupling reaction. All right, when we come back next time, we will talk about the Suzuki and the Heck reactions, which both involve these oxidative addition, reductive elimination steps. Okay. Oh, right. One last thing.